So today we're going to talk about rules of exponents. So first things first, you need to notice that the bases need to be the same in order for you to do anything between exponents. So for this first rule, I am going to look at multiplying two of the exact same bases, and I don't care if their exponents are the same or they're different. So for us to deal with rule number one, I would like you to first check out this particular problem. This x squared means I have two x's. This x to the fifth means I have five x's. Everybody's multiplied together, and it's multiplied between the two. So if I take a look, I basically have 7x's, which you would write as x to the seventh, wouldn't you? So the real question is, how do you go from the original problem straight to the answer without writing all these x's out? If you said add, you're absolutely correct. So what we're going to do then is we are going to keep the base the same because that's exactly what happened over here. I just dealt with the base of x, and then we get to go ahead and add the exponents together. Nice. Okay, let's look at the second one. The second rule, notice first and foremost the bases are the same, but now we're dividing. So in order to work the division, I want you to notice that we are going to look at the same problem. And now I'm going to take x to the fifth and I'm going to divide it by x to the second. Now, in this particular case, we're going to assume that the top exponent is the larger of the two exponents. So if I take a look at this problem, x to the fifth over x squared, that means we have 5x's on the top, and we have 2x's on the bottom. Since it's a fraction, I can basically reduce and cancel out 2x's, which would leave me 3x's on the top, wouldn't it? So, same question. How do I get from the original problem over here to the answer? If you said subtract, you're correct. Now notice, though, I would have to take the larger number, which is on top, minus the smaller number, and the answer would go on top since I had more x's on the top. So, in this particular case, my base is still the same because I dealt with all bases of x over in my example. And now I'm going to take the larger exponent minus the smaller exponent, and the answer is going to be in the numerator. Cool. Now, what happens if the roles were reversed? What happens if the bottom exponent was the larger exponent? What do you think is going to happen? Do you think it's going to be any different? Am I still going to subtract? If you said yes, you're correct. So take a look. What happens if now there's x squared on top and x to the fifth on the bottom? That would mean 2x's on top and 5x's on the bottom. And again, since it's a fraction, you're going to cancel. Now in this case, you're left with 3x's, but they're on the bottom, aren't they? Now what do you think is left on top? Well, remember, x goes into itself once and once, so that means there's a 1 left up here. So in this second half of rule number 2, you are still going to subtract your exponents. But since the larger number of exponents is on the bottom, my base remains the same, and I'm going to take the bottom exponent, and I am going to subtract the top exponent, and the numerator will just be left with a 1, just like it was in this example. All right, how you doing? So far, so good? Cool. Now, for some of you, this actually may be review, so if it is, wonderful. Hopefully, it's just a brief reintroduction, shall I say. Let's look at rule number 3. In rule number 3, I am dealing with one base and two exponents, and between the two exponents is this parenthesis. So recall what happens when you have any number with parentheses separating two numbers. What operation are you dealing with? You're right, multiplication. Well, no different with rule number 3. My base is going to stay the same And what's changing are my exponents, and I get to take the two exponents and multiply them together. And this helps with rule number 4, because in rule number 4, I still have my bases, A and B, but now notice this exponent on the outside now has two exponents on the inside to work with. Notice between the two bases is multiplication, and that's extremely important, otherwise you would not be able to do this. So since it is multiplication, I am basically going to distribute the exponent on the outside to the two exponents on the inside. So on the A, you have m times n, and on the B, you have k times n. Make sense? And it just piggybacks off that third rule. And by the way, this fifth one, same thing is happening. Just because it's division doesn't mean that my process is going to be any different than I did in rule number 4 or rule number 3. As a matter of fact, because it is division, I am allowed to take the exponent on the outside and distribute it to the two exponents on the inside, which, no surprise, leaves me these new powers on the A and the B. Loving it. How you guys doing? So far, so good? Cool. Okay, so let's look at number 6. On number 6, I usually ask what would be the potential answers, and I usually get 3 of them. I usually hear people say 0, and then I hear people say A, and then I hear people say 1. So let's check this out. And the way I'm going to get you to see this is by looking at 5 to the second power. Doesn't that just mean 5 times 5? This 2 tells me I have 2 5s. Well, if I notice this particular exponent, this exponent is a 0, which means how many A's should be in the answer? You're right, none, which means bye-bye answer number 2. Now, you're like, okay, well, I have 2 other options, and maybe there's another option, but in this case, we only have 2 options left. So, since there are no A's left in the answer, it takes out option 2. The one thing people need to remember is hanging out in front of this A multiplied by this A is this number 1, which means even though none of the A's are left in the answer, there's still this 1 hanging out, which means A to the 0 is going to be equal to 1. And that leaves us with this wonderful saying that you probably heard: anything to the 0 power is 1. And that's the reason, because there is a 1 hanging out in front here that people need to remember. Now, let's look at number 7. Here's something you need to understand. Negative exponents. Negative exponents. I need to write this because you need to see this. Negative exponents. Never, never, ever, ever make the answer negative. Never. Never, never. I can't stress never enough. So the job of the negative exponent is to tell you that the base is in the wrong place. In this case, the base is in the denominator, but this negative exponent says it doesn't belong there. That negative exponent says that my base should really be located in the numerator. So it gets popped to the top, so to speak. And now your exponent, now that it's done its job, now becomes a positive exponent, and it is in the numerator. Now, mind you, the 1 that was in the numerator stays in the numerator, and the operation between them now becomes multiplication. How you doing? Does this make sense? Okay, so let's look at this second half of it, shall I say. Again, notice I have a negative exponent, which tells me that this base is in the wrong place. Well, on the first half of it, the base was on the bottom, which means it needed to belong to the top. Well, in this case, the base is already on the top, which means that it belongs on the bottom. And when you move it to the bottom, the exponent goes positive because it's done its job. And you're like, well, great, now what's in the numerator? Well, here's the deal. Remember, what's hanging out front, waiting for you to recognize it? That's right, this 1. There is this multiplication by 1 out in the front. So it doesn't go anywhere because it doesn't have a negative exponent. So what goes on the top is the 1. How you doing? Does this make sense? Good. Let's put these into practice. Let's see what we get. So if I notice this first example, I am multiplying two of the exact same bases. We actually did this example, didn't we? So because I'm multiplying the two exact same bases, first and foremost, your base is not going to change. Your answer is still going to have the base of x. And what do you get to do between the two exponents? Well, if you notice on the previous page, that's rule number 1 here. We get to add the exponents. So I am going to take the 2 plus the 5, which will give me a final answer of x to the power of 7. Make sense? Cool. Well, let's look at example 2 then. In example 2, we still have to figure out if we can apply the same rule. First, I have multiplication between these two bases. Secondly, the bases are exactly the same, which is wonderful because that allows me to have in my final answer the base of y. And then what do I get to do between the two exponents? You're right, I get to add them together, which makes my final answer to be y to the power of 1, or we can just simply write that as y. Cool? All right, now let's look at the third example. Just because my bases are numbers doesn't mean I treat them any differently than I did problems 1 and 2. There's still multiplication here. My bases are exactly the same, which means in my final answer, I'm going to have the base of 3. And I get to add the exponents. And when I do this, I am going to get the final answer of 3 to the power of 3, which we can simplify to 27. Now, some of you get that just because we walked through it and knowing it was the rule. You're like, okay, fine, but I kind of don't buy it. So let me show you. We have 3 to the 5th. This power of on this second 3 being negative means it doesn't belong on the top next to 3 to the 5th. It belongs on the bottom, and now the exponent goes positive. And if I look at it this way, how many 3's are on top? That's right, I got 5 of them, all multiplied between, and the bottom has 2 3's. And because it's a fraction, I get to cancel, which leaves me 3 to the 3rd, which still gives me the exact same answer of 27. So regardless if your bases are numbers or variables, you do the exact same process. Make sense? Good, glad to hear it. Now, on problem number 4, notice I have 2 parentheses and I'm multiplying. And inside I have multiplication problems as well, which means I could really write this as 2 times a to the 6th times 5 times a. Now, here's the deal. This is them getting us to do 2 problems in one. This is them getting us to multiply the numbers together and then multiply our variables together. By the way, this second a doesn't look like it has a power, but it does. It's a 1. So you know as well as I do what 2 times 5 is. And based upon the first 3 problems, you know that when you multiply these two a's together, the bases are the same, you get to add the exponents. So when you write your final answer, since this was all multiplication, then my 2 individual answers are going to get multiplied together, which means I get 10a to the power of 7. Make sense? Cool. All right, let's look at number 5 then. Do you notice number 5 is basically the same problem as number 4? I have got a bunch of multiplication in between everything, and I am multiplying numbers together. I am multiplying A's together, and I am multiplying B's together. So they've given me 3 problems to work on. All right, so I am going to write the final answer, and let's see if you agree with what I've written. I am noticing the 2 and the 4, which is going to give me an 8. A to the third times a to the negative 4 gives me a to the negative 1. The b squared times b to the negative 5 gives me b to the negative 3. Do you agree with this? Wonderful. Now, I have negative exponents. Usually, unless they say otherwise, they don't want negative exponents written. So, does the 8 have a negative exponent? No, so it's going to remain exactly where it is. But the a with a negative power goes on the bottom. The b with a negative power also belongs on the bottom. And this is how they usually like you to write your final answer. Make sense? Okay, number 6, let's take a look. Do you notice I have a bunch of multiplication one more time? So this is not any different than what we've been doing, but I want to rewrite this on this. Inside this parenthesis, we have negative z to the third. Isn't that basically a negative 1 times z to the third? Okay, if you agree with that, then check out how I'm going to write my final answer and see if you agree. Are we cool? Loving it. All right, let's scoot on to the next problem. Now, notice in this particular case, in problem number 7, gratefully my bases are the same. So, and I'm dividing. So division turns into what operation? You're right, subtraction. Which exponent, or I should say, which location has more 4s? The top does. This one being larger means that when you start doing your work, you know your answer is going to have a base of 4. And it's going to be on the top because the larger exponent was on the top, and I subtract the smaller exponent, which will give me 4 to the power of 1, or just simply 4. Does this make sense? Cool. So it's the opposite of what we've been doing, right? Okay. Notice problem number 8. Problem number 8, again, is their way of getting us to do 2 problems in one. Because I'm noticing there's multiplication between the 24 and the x to the third, and multiplication between the 6 and the x. And since there's division here, it's basically telling me that I have this fraction of 24 over 6 multiplied by the fraction of x cubed over x to the power of 1. Some of you who are visual might actually like writing your problem this way, because it makes more sense. It visually makes more sense to people. And when I simplify my fractions, I get 4x squared. Larger exponent minus smaller exponent, and the answer goes on the top for those x's. How we doing? Making sense? Cool. All right, let's take a look at problem number 9. Bases are the same. My challenge is, though, I've got negative exponents. And something that hides the real problem are not only parentheses, but negative exponents. So I personally choose to rewrite this problem with positive exponents. So that negative 3 on the top tells me that this base of 10 doesn't belong on the top, it belongs on the bottom. And when I move it, its exponent goes positive. In the denominator, this base of 10 having a negative exponent, that negative exponent tells me it doesn't belong on the bottom. That 10 belongs on the top with a positive 5 now. And now I'm noticing that problem number 9 is just like problem number 7. So I get to take my base and I get to subtract the exponents, the numerator minus the denominator, because the numerator is larger. And when I do that, I end up with 10 to the power of 2, which will simplify to 100. Does this make sense? Cool. Getting the hang of it? Okay, knew you would. Look at number 10. Do you notice number 10 has multiplication in between the numerator and the denominator? So problem number 10 is almost like problem number 8, isn't it? Except it's 3 to work on. So, again, for us visual people, it might not be a bad idea to rewrite it as 3 separate fractions that you've got to work on. So, easy enough. 12/18 we're going to reduce by 6. The A's. I'm noticing in this particular case that I have more A's on the bottom. So that means my answer is going to go on the bottom. And I'm going to take the larger exponent minus the smaller exponent. That'll give me 2. And there's going to be 1 on the top because everything canceled out from the numerator. Now, on the B's, I'm noticing there are more B's on the top because it's got the larger exponent, which means my answer is going to have the B's on the top. And I do 3 minus 2, which is just going to give me a 1. So, my final answer is going to look like this. How you doing? Does that make sense? Love it. Okay, do you notice problem 11? It's kind of a combination of problem 10 and problem 9, because I have negative exponents, don't I? But I've got a bunch of multiplication going on as well, don't I? So what do you think I'm going to do first? If you said move those negative exponents, you're absolutely right. I do not want to deal with negative exponents because it's hiding the real problem. So the 21 has no negative exponent. It stays where it is. This x has a negative exponent, which means it goes on the bottom. This y, no negative exponent, stays on the top. This negative 7 does not have a negative exponent, so it stays on the bottom. This x to the power of 4, no negative exponent, it stays on the bottom, right where it is. And this y, having a negative exponent, says it doesn't belong on the bottom, it belongs on the top. And its exponent goes positive. Okay, so again, for us visual people, like we did in problem 10, where we separate them into 3 fractions, some of you might want to do that. See if you follow along with me as I write the answer. Does that make sense? Cool. Loving it. All right, let's see what else we got. Okay, here we go. I have got a single base here, and I've got parentheses separating 2 exponents, basically separating 2 numbers, which means what do you get between those 2 numbers? You're right, you get to multiply them together. And so, here's the thing. The base is not going to change. Your exponents are going to get multiplied, which means your final answer is going to look like 3 to the power of 6. And I know somebody is going to ask, well, can I leave it as 3 to the power of 6? Well, sometimes yes and sometimes no. It just depends on the directions. If they say to simplify it, that means you're going to simplify it to 729. Now, I'm going to show you a little bit of a different way of looking at this problem because for some people it might help. This 3 being on the outside means I have 3 parentheses. And inside each parenthesis is 3 to the power of 2. So if you take a look at it this way, I would simply keep my base and I get to add all three of these exponents together, wouldn't I? Which still gives me 729. All right, so that was just a second way of looking at it in case somebody needed an alternate way. Now, same thing on number 13. I've got a number on the outside of these parentheses, which means I get to distribute exponents to exponents because that's how it works. And you're like, well, the 4 doesn't have an exponent, so it doesn't get distributed. Not quite. The exponent, or the 4 does have an exponent. That exponent is a 1, which means this 2 on the outside gets to be distributed to that power of 1, which means I'm going to have two bases. One is a 4, one is a y. The powers, on the 4, it's going to have a power of 1 times 2. On the y, it's going to have a power of 2 times 2, which means my final answer is going to be 4 to the second times y to the power of 4. And yes, you will have to simplify 4 to the second because that's a simple enough problem to work on, and they won't even have to say simplify that. Does this make sense? By the way, let me look at this just a little bit differently. This power of 2 tells me I have two parentheses, and inside each parenthesis is a 4y squared. And if I do this the long way, I'll do 4 times 4, which is your 16, and y squared times y squared, which is y to the 4th, which gives me the exact same answer as we got using the law of exponents. How are we doing? So far, so good? All right, so let's see if you follow along with number 14. I'm just going to distribute. Do you agree? Wonderful, because it's just like problem number 13, isn't it? Except I have division between the two bases. And I do need to simplify 5 to the power of 3. Okay, so let's look at problem number 15. Let's see if you follow along with problem number 15. Does that make sense? Remember, the powers, even if you don't see them, the 2 has a power of 1, the x has a power of 1, just like on problem 14. The 5 had a power of 1, the x had a power of 1, which means when I distributed, I was basically doing 3 times 1 on problem 14. But on problem 15, I'm doing the 5 times the 1s. Okay, there's one thing I have to simplify, though, in problem 15 before I can move on. How's that? Does that make sense? Loving it. Okay, so let's look at problem 16. Now, you're like, well, it's the same thing. I'm going to be distributing. And you're right, you are going to be distributing. However, I'm noticing something. This is a fraction, and I'm noticing this 2 and this 6. Since it's a fraction, I'm noticing that I could reduce those. The 2 will go into itself once and then into 6 3 times. So I'm noticing that I could make my problem just a little bit nicer looking for myself. Does that make sense? Yeah, if I can simplify inside the parentheses first, I'm going to. Because according to the order of operations, parentheses always come first. And if I can simplify, I'm going to. So let's see now if you follow along with what I'm going to write as my next step, but not my final answer, because I need to simplify the 3 to the power of 4. And now here is my final answer. How are we doing? Does this make sense? Are you agreeing? Loving it. All right, let's look at number 17 then. We have a lot going on here on problem 17. We have got exponents on the outside, and to boot, these exponents are negative, aren't they? So, you know, there's a couple of different ways you can handle this. I am going to distribute my exponents first because That usually seems to be the easiest thing to do regardless of the type of problem they give you. Because if you look at number 20, if you look just ahead of number 20, there are a lot of things going on. There's a negative exponent on the very, very outside and on the inside. So the best way to handle these type of problems is to just go ahead and distribute these exponents on the outside. So when I do, I am going to get this next step. So let's see if you agree. Did that make sense? All I did was take my exponents on the outside and distribute to the exponents on the inside. And now I'm noticing I have a lot of different negative exponents, and I do not want to deal with negative exponents because they're hiding the real problem. So negative exponents tell me these guys are in the wrong places, so I'm going to move them. So this m, does it belong on the top? You're right, it does not. It belongs on the bottom. And when it comes to the bottom, the exponent changes to a positive. You're like, hey, well, you forgot the negative. Well, let me ask you something. Isn't that negative going to make the entire answer negative? Then I'm just going to move it to the outside to make life just a little bit easier for us. Now notice this n. Does it have a negative exponent? Yes. It's on the top, isn't it? Does it belong there? You're right, it does not, which means I'm going to move it to the bottom and its power goes positive. Now let's look at the m on the bottom. Does it belong there? You're right, it does not. It belongs on the top and then its exponent goes positive. This n on the bottom, you're right, it moves to the top and now its power goes positive. And now when I'm going to simplify this, I'm noticing it's like another problem that I've already worked on the previous page. And I am going to write my final answer as negative m to the power of 5 over n, which has a power of 1. And the answer is negative. Cool? Loving it. Okay, problem 18. Let's see what we got going here on problem 18. What do you think I'm going to do first? You're right. I am going to simplify the inside because I'm noticing this 5 and this 3, or I should say this negative 15 and this 3. I don't want to deal with that. So that's going to give me a negative 5 on the top, isn't it? Right. Do you notice I have a negative exponent on the bottom? I think I want to move that while we're in here working to try to simplify the inside. So I have an r squared on the top. I have a t on the top. And now this r to the negative 3 on the bottom, that negative tells me to move the r to the top, and it's multiplied. And I still have a t to the 4 on the bottom. And I still have this power of 3 on the very outside. Do you agree? This moving is just like we did on one of the previous problems on the previous page. So if I'm taking a look, I get to simplify inside again. I have negative 5 on the top. This r squared, this r to the third, both being on top means I get to add my exponents. This t on the top and this t to the fourth on the bottom tells me I get to subtract. And since there are more t's on the bottom, that means my answer is going to go on the bottom when I subtract. And then I have the power of 3 on the outside. Does that make sense? Okay, so let's see. Here is my next step to get my answer. The inside is so much nicer looking at this step than it was on the original problem. I have now negative 5 to the power of 3. And notice, the negative 5 is in the parentheses. That whole number gets to the power of 3. R is going to be to the power of 15. T is going to be to the power of 9. And when I write my final answer, I got negative 125 r to the 15 over t to the power of 9. Does that work for you? Cool. Okay, so notice number 19. Order of operations. Tells me to do parentheses first. Well, there are no parentheses here. And then it tells me to do exponents second. So I'm noticing I have exponents. But you know, something the order of operations forgot to tell us is after the first level of parentheses, the second level is exponents. But with exponents goes its opposite, which is roots. Exponents and roots are opposites of each other. So you have to work the problem left to right when you see both exponents and roots. When I come in from the left, I'm noticing the first thing I see is this square root, which means I've got to take the square root. But I can't take the square root until I figure out what I'm taking the square root of. So my square root's going to remain because I don't know what I'm taking the square root of because I have an addition problem inside. I'm going to have to simplify this addition problem first before I'm allowed to take that square root. So in other words, this particular square root sign is almost acting like a parenthesis saying, hey, do what's underneath first and then tell me my answer, which you know as well as I do, your answer will be a 5. All right, so problem number 20 looks like a whole lot of fun. So let's see if you follow along with what I'm going to do here. Do you see what I did? You're right. I took care of these inside parentheses first by distributing the exponents on the outside. Okay. Let's see if you follow along with my next step. Do you see what I did? You're right. I simplified the 2 to the 3rd, and the y to the negative 6th power being on the bottom says it belonged on the top, so I moved it. Okay, so far so good. Let's see if you follow along with my next step. See what I did? You're right. I did reduce the 4 and the 8. The x's I also reduced because there was subtraction that I had to do between the powers since they were divided. It left me 1x on the bottom. And the y's, since they were together on the top by multiplication, I got to add the y's together. Okay, how we doing? All right. So I'm going to take the problem this way. Let's see if you follow along with my next step. You're right. If you notice, I took the power on the outside and I distributed to the powers on the inside. Okay, so far so good. See if you follow along with my next one. You're right. All I did, if you notice, is I took each base that had a negative power and I put it where it belonged. This y belongs on the bottom. This 2 and this x both belongs on the top. And last but not least, I am going to simplify that 2 to the power of 2, which will leave me a final answer 4x squared over y to the power of 16. And there we have it. I took each step slowly. Why? Because there was a lot going on. So I suggest that you take a problem as in number 20, step by step. Don't try to combine 2 steps in one. How we doing? We all right? Okay, so now, in terms of what's next, is we are going to look at scientific notation. And why do they put scientific notation here? They put it here because it basically is dealing with exponents. And we have to do things between exponents, add, subtract, multiply. So we're going to take a look at scientific notation. Notice the definition I wrote. Scientific notation only allows one number to the left of the decimal point, and that number cannot be a 0. Why can it not be a 0? Because a 0 doesn't have any value. So if I take a look at 150,000, first and foremost, I better identify what this decimal point is. So think of money. Wouldn't that be that decimal point be to the very right of the number? And scientific notation says only one number is allowed to the left. Well, I've got 6 numbers to the left of this decimal point, which means I got 5 too many, which means your decimal point belongs between the 1 and the 5 here. That would mean that 150,000 is the same as 1.5. And you know as well as I do, it's not the same. So we're like, great, how do I compensate for what we've done? Well, we got to know what we've done here. We have skipped 1, 2, 3, 4, 5 places, and we need to understand what these 5 places are that we skipped. I understand this is the ones place, this is the tens place, this is the hundreds place, but can't I just write that as 10 to the second? This is the thousands place, but couldn't I write that as 10 to the third? And then here's, you're getting the hint, the idea, that's 10 to the fourth. Well, isn't the ones place just 10 to the 0? So I skipped 1, 2, 3, 4, 5 places, and each place is a value of 10, which means to get 150,000 into a shorthand notation, a reduced notation, I am going to take this 1.5 and I'm going to multiply it by 5 places of 10, because I skipped 5 places of 10, which means my final answer will be 1.5 times 10 to the power of 5. How are we doing? Does that make sense? Cool. All right, let's look at this other one. Now, in the second number, I've got 0.0007. My decimal point does have one number to the left, but up in the definition it said it cannot be a 0, which means I can't leave it there. So the only viable number I have is this 7, which means this decimal point needs to move all the way to the right of the 7. So I have one number to the left of the decimal point, and it's not a 0. But again, you have to compensate for what you do. You know you're going to rewrite this as 7 point, or you just write 7. But you've got to realize you skip places of 10. Now here's the deal. This is the 10th place, right? This is the 1/10th place, isn't it? Well, we write this as 10 to the negative 1. This is the hundredths place, which is the negative second power. This is the thousandths place, which means I'm going to multiply by a base of 10, and I skipped 1, 2, 3 places, but I skipped them in the negative direction, which means my final answer will be 7 times 10 to the power of negative 3. How are we doing? Does that make sense? All right, so let's look at these next 4 problems. Actually, the next 2 problems. They want us to write in scientific notation. The first one says we have 50 million tweets. Okay, I don't know who has 50 million tweets, But then again, I don't tweet. So, but we need to know how to write 50 million. You know you're going to write 50. Now, million. If I put 3 zeros, that's 50,000. If I put 3 more zeros, that's 50 million, isn't it? And you know your decimal point's going to be over here to the very right. Well, you know as well as I do, I got too many numbers to the left of that decimal point, so let's see if you follow along with what I'm going to do. 1, 2, 3, 4, 5, 6, 7. I skipped 7 places of 10, and because I went to the left, these numbers, these powers, get larger. Cool. Let's see if you can follow along with what I'm doing on the second one. My decimal point is there, 2 places, which means I'm going to have 3.8, and I know I skipped places of 10. I skipped 2 places of 10, but when I move to the right, the exponents are going negative. Does that make sense? Cool. All right, you guys are doing great. Now, in this next 2 problems, they're asking us to write them in standard form. Another word for standard is decimal form, which means we do not want scientific notation. And when you take a look at problems 1 and 2, the scientific notation is given away by this times 10 to whatever power. Because we don't write numbers like that. We write numbers like we do in numbers 1 and 2. And even these original 2 examples over here. So, I need to get rid of this 10 to the 4th power. Well, if I look at 150,000, as I move to the left, the powers increased and they were positive, which means I got to move to the right to undo it. So I have 5, and my decimal point is to the right of that 5, but I need to move to the right to get rid of this power of 4. 4 places to the right, and I have empty spaces, which means you get to fill them in with, zeros, because 0 is my placeholder when it comes to numbers, which means your final answer would be 50,000. Remember, I moved to the right because this original power said I moved to the left. Okay, so look at problem number 2. My power is negative, which means I originally moved to the right. So, to undo the move to the right, you've got to take your decimal point and you've got to move it to the left, and in this case, 3 times, which means, again, I have empty places, so I need to fill them in, and I fill them in with zeros, which means my final answer is 0.0041. How you doing? Cool? All right, so let's look at this next and last page. Now, problem number 1 here. Do you notice this is 2 times 10 to the 4th and 3 times 10 squared, and it's multiplication implied between the 2 parentheses? Well, notice up here in this problem I wrote in blue, isn't there multiplication between the 4 and the b to the 3rd, and multiplication between the 2 and b squared, and multiplication between the parentheses? What I'm saying is this problem in blue is exactly the same as this first problem that we're trying to work on. But we just worked on this problem in blue. I would do 4 times 2 first, wouldn't I? Well, what am I going to do first in problem 1? Hopefully you said do 2 times 3 first. And back to this problem in blue, I would then tackle these bases of b, and I would add those exponents. Well, I'm going to tackle these bases of 10, and I am going to add the exponents. And since there's multiplication, I am going to multiply my 2 answers together. So, my final answer on problem 1 would be 6 times 10 to the power of 6. Easy peasy, right? It's just like the other problem, the one in blue, the one we just did up here, which is a problem that we did like 3 pages ago. By the way, I need to make sure if they say put the answer in scientific notation, And I need to make certain my answer is in scientific notation, which means I'm only allowed one number to the left of the decimal point. And since my decimal point is there on the 6, we're good to go. There's only one number to the left. Okay, so look at problem 2. Is problem 2 going to be any different than problem 1? You're right, it won't be. So first thing is 5 times 4. Second thing is my base of 10. I get to add the two powers together since they're multiplied. And then I get to multiply my two answers together, which will give me 20 times 10 to the power of 2. Now, is the answer in scientific notation? Well, my decimal point on the 20 is there to the right of the 0. And I got two numbers to the left of the decimal point. Scientific notation says only one number to the left, which means I've got to take my decimal point and I got to move it one place, and I'm going to move it over to the left. And when I go to the left, my numbers, my powers of 10 get larger, which means I get to add 1 to this power of 2. I have to compensate for that move. Therefore, my final answer will be 2 times 10 to the power of 3. Does that make sense? One more time. I had to take this decimal point, I had to move it to the left 1, and when I move to the left 1, all these powers of 10 start getting larger and larger. It increases. So I had to add 1 to compensate for moving 1 to the left. Good? Okay. So look at number 3. Number 3 is basically the same as 1 and 2, except instead of multiplying my two numbers, I get to, you're right, divide the two numbers. And instead of adding my two powers, in this case, since they're divided, I get to subtract. And by the way, in scientific notation, you always take the numerator minus the denominator. Always. So, in this particular case, I am going to do 6 divided by 2. And I'm going to take my base of 10 and the numerator minus the denominator, and I get to multiply my two answers together, which will give me 3 times 10 to the power of 2. And since 3 is the only number to the left of the decimal point, this answer is good to go. Okay, so let's look at this other one. Again, I have to do 2 divided by 8. I take my base of 10, I take the numerator exponent, and I subtract the denominator's exponent. And then I get to multiply the two answers together. All right, so 2 divided by 8, well, that's 1/4. And now I'm subtracting a negative. This double negative will make it a positive, won't it? Which means I'm going to rewrite this fraction because scientific notation doesn't deal with fractions. It deals with decimals. So I'm going to rewrite that decimal. Does that make sense? All right. Now I'm noticing this decimal has no numbers to the left of it, which means I am going to have to take my decimal point and go to the right one space. And when I go to the right one space, just like we did on this previous problem, when I go to the right, my exponents start getting negative, and they start -1, -2, -3. They start decreasing. So 1 to the right means I get to subtract 1, which means my final answer will be 2.5 times 10 to the power of 2. Now you know where they put scientific notation with these exponents, because we are still dealing with exponents by adding them, subtracting them, and even adjusting them. Hopefully this helps. Hopefully you have fun with exponents. Catch you on the flip side.